is we're going to be now exploring how an epsilon NFA actually works. So how does an epsilon NFA work? So in plain language, I'm just asking how it works. So you naturally will know if we see what an NFA and a DFA does in a more exact way. It means we're going to have to define an extended transition function that tells us how computations on the machine are carried out. But to do that, to answer this question, I'm going to introduce a concept called an epsilon closure. So to answer this, we use the concept of a epsilon closure of a state. So we're going to define this concept of an epsilon closure of a state. So what this is going to represent is how we allow the transitions to freely occur without consuming or reading a symbol. So epsilon closures are going to capture this behavior. So I'm going to denote this. I'm going to call this eClose Q. So if I give you, so this is a state, I give it to you, it gives me back a set of states. So informally, so I'm going to define it formally, but informally, eClose of Q, so for state Q, returns all states that can be transitioned to by epsilon, the empty string, via state Q. So like I said, we give that option. The epsilon NFA will use an epsilon closure to get to those states freely. So that's the intuition behind this. So let me define this a little bit more carefully. So once I define it more carefully, we'll see some examples. So epsilon closure. So define eClose Q inductively as follows. So we're going to define it inductively. So we're going to have a base case, and then we'll have an inductive part. So the basis of the definition is that state Q must be in eClose of Q. So anytime I give you a state Q, it has to be by definition that eClose of Q contains Q. You might say, why? So these are states that can be transitioned to by epsilon. And we already know that if you just don't consume a symbol, for free, you end up in the exact same state, right? So this makes a lot of sense, right? So the inductive part is if P, so if a state P is in eClose Q, then so are all states in delta P epsilon. So it means that when you transition on epsilon, any of the states that you get as a result of that also have to be in eClose. So one other detail I want to add, just as a note. So we can also define eClose on a set of states too. Given a set S of states, e-close of S is just simply going to be the union of all. So I'm going to take all of the resulting epsilon closures on the states within this set. So we're going to do an example, some examples seeing how epsilon closures work. One remark I do need to make is that if you give me an empty set and you apply epsilon closure on that, it still is an empty set. Just keep that in mind. So let's do an example. So let's try applying this definition. So we're going to try applying epsilon closures on various states of this epsilon NFA, just to see what happens. So 1, 2, 3, 4. We're going to have 6 states, where 5 is going to be the final state. So I'm going to have an epsilon transition from 0 to 1. I'm going to have an epsilon transition from 0 to 2. I'm going to have an epsilon transition from 1 to 3. I'm going to have an epsilon let's make it an A. Make it so it reads an A. It goes from 2 to 4. Let's make it so it reads a B. You can go from 3 to 4. But we'll make the rest here epsilon transitions. So from 3 to 5 and from 4 to 5, those are epsilon transitions. But I'm going to allow it to keep reading B's once it's in state 5. so let's see what happens. So what we're going to do is we're going to see what epsilon closure does if I give it a state. And then we'll see what happens if I give it a set of states, just so we can see some examples of how this works. So let's consider the epsilon closure of state 0. So what would this be then? So first, we know that the state itself is a part of this set, right? So we know for certain state 0 has to be in this set. That's what the basis of the definition says. Now, this is where it gets a little tricky at first, because you also have to think about this carefully, because this definition is inductive. Or in other words, you can think of it as recursive if you think about like a process that keeps occurring until this definition is satisfied. So if there's a state that's going to be an e-close of Q, then so are all states in this, right? That's what it says. But what does that mean then? What does that mean then? So it says if that's an e-close of Q, then so are all the states in this. But what does that mean? That means that if I apply an epsilon closure on a state, I end up with potentially more states. And those states also, if they are a part of this, then so are those ones on transitions with epsilon. So you're going to see quite quickly that every time you do this, you can see that it's essentially a process where I'm just going to keep accumulating all of those epsilon transitions from each state I discover. So just as an example, if you were to just literally just interpret if P is in this, so if 0, so now I want to walk through what this means. So if you imagine you're given a state of the epsilon NFA. So if it's saying if 0 is an epsilon closure Q, then so are all the states that you could transition to. So if 0 is in there, then all the ones that you could transition to on 0 using epsilon also are as well. So watch this. So that means that 1 is, and so is 2. Because notice there's epsilon transitions that get you to these states. But now, notice that I have states 1 and 2 in the set. So if 1 is an epsilon closure, because remember, it's a conditional statement. So if 1 is in e-close of this state, then so are all of its states that you could transition to on epsilon. So notice that 1 could transition to 3 on epsilon, so 3 is also in here. Now 2. notice that there's no epsilon transitions here. You just end up with 2, right? So, we're done with 2. How about 3? So if 3 is an epsilon closure Q, which it is presently, then so are all the other states that you could transition on that state with Q. And sorry, with P, which P is 3 here. So I have epsilon, so I can go to 5, right? But notice I can't go to 4. Notice 5 doesn't have any transitions that head outward to a different state. So you know that this is actually the epsilon closure of 0. So you keep repeatedly applying the inductive definition here. So every time you discover another state, if that is indeed a part of this set of states, then so are all of the so all the states you could reach via an epsilon transition. And you keep repeatedly applying this process. Let's do another example. Let's consider epsilon closure on state 1. So if I look at state 1, okay, 1 by definition is in the epsilon closure of 1. But notice there's an epsilon transition, 3. Well, if 3 is a part of the epsilon closure of 1, then so are all the transitions on state 3 given epsilon. So notice that I can go to 5, right? But I can't go to 4. So that's the epsilon closure of 1. Let's continue. Let's try the epsilon closure of state 2. So notice that 2 by definition is in the epsilon closure of 2. But notice there's no epsilon transitions. So if I just give you epsilon with that state, it's not going anywhere. So notice it's just 2. How about epsilon closure of 3? Okay, so now, akin to our previous example, 3 by definition is in the epsilon closure of 3, of state 3. There's an epsilon transition to 5, but nothing to 4. Notice there's nothing outward that direction. So this is the epsilon closure of 3. How about the epsilon closure of 4? So state 4. So what would be the epsilon closure of state 4? What would it be? Well, notice that there's an epsilon transition from 4 to 5. So 4 by definition is in the epsilon closure of 4. Notice there's an epsilon transition on 4 to get me to 5. Nothing leaves 5. So that's the epsilon closure of 4. How about epsilon closure of 5? Well, 5, there's nothing outgoing from 5, but by definition, 5 is in the epsilon closure of 5. So now we've examined all of the states. Let's do an example where I give you a set of states. So suppose I defined the epsilon closure with a set of states. Suppose I give you states 2 and 5. Well, this is actually equal to the epsilon closure of 2 union the epsilon closure of 5, right? That's what we defined the epsilon closure of a set of states is. So E close of 2 is just 2, right? So this is just 2, the set containing state 2. And how about 5? How about 5? Well, it's just 5, right? Just the set containing state 5. So if I take the union of the result, I end up with just the set containing states 2 and 5. And that's it. So that's how epsilon closures work. So now that we have this mechanism that models these so-called epsilon transitions that we've talked about, let's now define the extended transition function using epsilon closures. So once we have this, we have a way of defining the computations of an epsilon NFA. And you're going to see very quickly that this is not going to be very much different than what we had with the NFA. It's just, we're going to add this mechanism into here. So the extended transition function the extended transition function for epsilon NFAs is next. So let's define this together. So just like what we had for extended transition functions before, this will be defined on a string, not just a symbol, or the empty string in our case as well. So the extended transition function and I'll use similar notation as before. Function delta hat is defined as follows. So there's nothing going to be really surprising about this example here. It's just going to be that we're going to have it where we're going to incorporate these epsilon closures. And I want you to really identify those parts that are different, because it'll give you an intuition for the relationship it has with an NFA and perhaps a DFA. So we're going to have the basis. So the basis is just simply that delta hat. So if I give you epsilon on a given state, well, what would we need to incorporate here? Well, if it was just an NFA, right? This would just be the set of states that just contains Q, right? It's just a set with the Q in it, right? That's what would happen with an NFA, a vanilla NFA. What would be different here for the epsilon NFA? Well, it's allowed to transition on those epsilon transitions, right? It doesn't have to read a symbol. So that means it can be on an epsilon closure of that state. The inductive part of our definition for delta hat is as follows. So first I'm going to I should probably describe it first informally, and then I'll describe it formally. But there shouldn't be anything too terribly surprising here. Less formally, after computing the set of states as in an NFA, epsilon closure is applied. Epsilon closure is applied to all the resulting states. So let me describe this more formally now. Suppose, so the string W is of the form W is equal to XA, where A is the last symbol of W, and X is everything but A, where A is the last symbol of W. And akin to what we talked about with an NFA, we're going to let delta hat, given a state to start off with Q, where I read off X. Suppose it gives me a set of states, P1, P2, all the way up to PK. Then it has to be the delta hat QW. So delta hat on state Q, when I read W, what would it be? What would it be? Well, what did it look like for an NFA? So remember, we compute the set of states like we would for an NFA first. And then what we do? We apply an epsilon closure. So how did we do that for the NFA? Well, over each one of these states, so each one of these, P1 all the way up to PK, you'd apply the transition function. All the resulting sets of states all get lumped together via union, and that's the resulting set of states for an NFA. However, now the wrinkle is that yeah, we could transition for free on the epsilons, on epsilon, right? So that's quite naturally going to get modeled into this. So let me just write out the part for the NFA part. So for each one of the states, I transition on A, give me a set of states, and then what happens is I apply the epsilon closure to the resulting set. So now that we have the extended transition function, this tells us exactly how it's going to compute strings for the epsilon NFA. I can now define what the language of an epsilon NFA is. So now that we have this, what I want you to do is go back to those previous examples that we had for epsilon NFAs, and I would like you to try out some strings using this definition akin to what we did with the NFA. So give that a try. But I want to define one last thing for us, is the language of an epsilon NFA. It's not going to be very terribly surprising, akin to what we talked about with an NFA. So given epsilon NFA E, which is going to be equal to, actually I'll write E over here, NFA E. So if I give you a set of states, set of input symbols, delta Q0F, then the language of the epsilon NFA is the set of strings, language, such that delta hat Q0W, how did we define it for the NFA? Well, it was this. We wanted to make sure that there's at least one state in here, in the set of states, that is one of the final states, right? So we take it in and intersect it with F, meaning that now if this is a non-empty set, the result means that there's at least one element in common among the two, meaning that there's at least one state in F that belongs into this set as well. As long as that's not empty. But yeah, this is the language of an epsilon NFA. And now that you have this, now you can talk about claims all about how you recognize some language. You can pick up all the tools that we've discussed previously for NFAs and DFAs and formalize it a little further. Say, for example, you want to pick up this and prove the correctness of the epsilon NFA. You can use some of the techniques we've seen before using this definition of the language of that epsilon NFA.